Okay, how many types of polarization are there? What is polarization? Polarization is nothing but it is dipole moment. Dipole moment per unit volume is called as the polarization. Polarization is exact meaning of that. Okay. So now what is dipole moment? Dipole moment mu is equal to, fine. So yesterday I have taught you the dipole moment is nothing but it is the q, the charge of one pole multiplied by the distance. Let us say this is the dipole. Okay, this is positive q, negative q separated by some distance L. Okay, so what is the dipole moment? Dipole moment is q into the distance is called as the dipole, and dipole moment per unit volume is nothing but the polarization. Okay, now how many types of polarizations are there? The first one is there are 4 to 5 types, but main categories are 3 types. We have electronic electronic polarization. Okay, the second one is ionic polarization. Third one is orientational orientational polarization. There are 3 types of polarizations. The name itself says some books they have given 4 types, some books they have given 3 types, but main types are only 3 types: electronic, ionic, orientational. Okay, the name itself says some hint what may be the electronic polarization. Okay, here in the first case, that is electronic, in the case of electronic polarization, we will consider the atom. We will consider an atom. Say this is the atom, this is the atom. Okay, we have the atom. So in this, the positive center is nucleus, that is exactly at the center. Okay, and electrons will revolve around this. Electrons will revolve around this. So this is an atom. Fine. So this is the before application of the electric field. We have not applied any electric field to this atom. Okay, I'm considering the single atom wherein electrons are there. Since this we are applying the electric field on electrons particularly, so this is called as electronic polarization. So this we have to separate it out. Fine. So this positive center should come at one side and negative centers should go one side. Fine. So now, well, let us apply the electric field to this atom. At that time, the effective center of this positive field will go one side and the effective center of the negative will go another side. It is going to happen like this. Okay, when I apply the field to this, when I apply the field to this is positive, this is negative. Okay, then here it is E is greater than 0, or you can say the E is not equal to 0. So when I apply the field, it is going to happen in this way. So this is applied in case of monoatomic gases. Is applied in the monoatomic atomic gases. That means the gases which are having only single atom. In those cases, this is applicable. This is applied in that case. So what happens? Just let us analyze this. What happens is charge distribution. This is called as charge distribution. At the center we have nucleus, and charges are distributed around that. And when applied, the charges are shifted to one side, nucleus is shifted to another side. So how can the nucleus can shift to another side? So as we know the electron should revolve around this. Electron should revolve around the positive positive nucleus. But in the diagram, what I have shown is electrons are one side and the nucleus is another side. So this cannot be the structure of the atom. Let us let us let us. I'll just tell you why we have shown it like that. So it may be like this. So we have this nucleus at the center, and electrons are revolving like this around this. Okay, electrons are revolving like this. Fine. This is at the center, nucleus is at the center, and electrons are revolving around this. So as soon as when I apply the field, what happens is it will if this is a nucleus. Okay, the electrons will shift slightly like this. These are revolving only, but those are shifting. Those will shift like this slightly. Those will shift, right? So like this we can take the meaning of this diagram. Okay, but when it is only when the field is applied. Fine. Next, the displacement. What happens is displacement or separation of the positive and negative charges takes place. What happens is displacement displacement takes place of positive and negative charge centers. Okay, and which leads this leads to what? This leads to develop. Okay, this leads to develop the dipole moment. Dipole moment. Okay, we have two poles now. We have two poles here, right? This we can take as one pole, this we can take another pole. Then there will be a development of the dipole moment. As we have developed the dipole moment, there is a polarization. Okay, if I consider the whole material monoatomic gas, I cannot consider a single atom. I have to consider the gas itself, some volume of a gas. To some volume of a gas, if I apply the field, then all the atoms will align in this manner and polarization will take place. That polarization is given as it is alpha E. Alpha E is equal to epsilon naught epsilon r minus 1 divided by n. Okay, what is n? N is the number of atoms per unit volume. N is it is the number of atoms per unit volume is the n. Okay, don't bother much about these equations. You have to explain with the diagram neatly. That is more than enough in the examination. Okay, there are some few equations that I'll discuss. So this is the first type. This first type is the electronic polarization. That is the first type. Now the second type. What is the second type of polarization? What is the second type? Second one is it is ionic polarization. It is ionic polarization. Okay, this is second one. The name says it is ions. Then there should be ions inside the material. Okay, that means for example the salts like NaCl or KCl, okay, etc. These are the salts. When I take this in the water, it will dissociate as ions. Okay, such a materials we should take, and we are not taking water. Direct whole material only we are taking. And for example, these are the positive ion. This is a negative ion. This is a negative. This is positive, negative, positive. Like this, it will be moving around. Okay, these are the, let us say these are the ions. Okay, these are the ions. This is at electric field is not there. We have not applied any electric field still. Fine. So when I apply the field, what happens is, let us take this in between two plates. In between two plates, if I take and if I make this positive and negative, these ions will be aligned in such a manner. This is negative, this is positive. Okay, these will be aligned in this manner. This is negative, this is positive. Where all there itself, those will align. If it is here, then it will align in that position only. If it is here, it will be aligned in this position only. If it is here, it is going to align, because this is solid material. Okay, this is not liquid or a gas material to go and attach to this plate. This is the solid material. Okay, where all it is there, it is going to rotate, or it is going to attach. Okay, these two are here, and those will become the poles, dipole. And this is called as the polarization in case of ionic materials. Okay, this is E is not equal to 0, or you can say E is greater than 0. This is in absence of electric field. This is in presence of electric field. Okay, so this ionic polarization happens in case of ionic materials, such as these are the salts. There are so many salts in that cases, this ionic polarization will happen. Okay, so here what happens is ions undergo ions undergo displacement. Okay, and it is insensitive to temperature. It is not dependent. The polarization in this case, it is not dependent on the temperature. Fine, it is not dependent, or you can say insensitive to temperature. Okay, if I increase the temperature of this system, then it is not going to cause any problem to this polarization. Okay, polarization will be same if I increase the temperature also. Fine. So in this case, this alpha I is equal to, so I stands for ionic polarization. Okay, then this is P. Alpha stands for polarizability. Alpha is polarizability. P is polarization. Okay, so this is PE divided by NE. So don't bother about this equation. So we will solve that in the derivations. The third one is orientational polarization. The third case is orientational polarization. Third one is orientational. Orientation means the alignment of the direction. Now here we'll consider the long chain molecules. Okay, for example, this is the long chain molecule. Okay, the molecule is represented in this manner. Fine, I have taken the molecule in this manner, and these are aligned in randomly. Anyhow, these are aligned randomly like this. Okay, these are random alignment of the molecules. Okay, so when this is field is 0 over here, when I take these molecules under the plate, when I take molecules under the plate and apply the field to that, that means E is greater than 0 here. So at that time, this molecule will orient in this direction. This molecule will orient in this direction. So this is the molecules. Okay, these are the molecules which orient in this direction of the field. Okay, so this is called as orientational polarization. So what happens here? Occurs with the permanent dipole moment. So this indicates the molecule has already dipole moment. So already my dipole moment it has got. The molecules or the materials which have the permanent dipole moment, with that only the orientational polarization is going to happen. Okay, that means what should be the point? The point should be it occurs with permanent dipole moment, with the permanent dipole moment. Okay, and the randomly aligned molecules are oriented. Okay, earlier those were random molecules will align in one direction, will align in the field. Okay, in the field these will be aligned. Fine, and it develops the polarization. It develops the polarizability. Okay, the increase in the temperature. If temperature is increase in the temperature, what happens is what happens is the polarization will decrease. That means when I increase the polarization, these alignments will disturb. Alignment will be disturbed. That means what happens is the polarization decreases. Right? As I increase the temperature, the polarization is going to disturb. Right? So this is the orientational polarization, and the polarizability is given as alpha naught mu square divided by 3 kt. Right? So three types we have seen today. The first one is electronic, second one is ionic, and third one is orientational. So they have asked a couple of times this types of orientations, types of polarization with the diagram for 6 marks. Okay, you need to explain these points, what happens with the temperature, how it is going to align, and with what molecules it is going to happen. So this is the types of polarization. Any doubts do you have? So this is very basic thing I'm telling, and very slowly I'm telling. Yeah, any doubts? If you don't have doubts, then I'll take another concept, and then I'll try to electronic polarization E naught. We can take any symbol. We can take any symbol. What I have taken is electronic polarization. Yes, orientational polarization. This is E naught or alpha naught. You can take any symbol. You can take. Some people they'll take alpha I, alpha O, and alpha E. Now you can take E naught also, polarization, electronic polarization, right? It's not a problem. We will see that. Okay, so that what happens is the total polarizability alpha is equal to. So in the material, if you take any material, so that will be including electronic plus ionic plus the orientational. So this is the total polarizability. Okay, this is the total polarizability of that material. So if you take alpha E, alpha I, and alpha naught, it's a total thing. Yeah. Then now we will see the internal fields. Internal fields in the liquids and solids. Internal fields. Internal fields. So it happens the internal field is developed only in case of liquids, only in case of liquids and the gases. Okay, first we will understand what is the internal fields. What is internal field? Okay, so if I take any material, for example, I'll just draw the diagram like this. For example, this is the one material which is having the, we can take this as an atom or a molecule. Some material is there, some material is there like this. Fine. So to this, what I'm going to do is apply the field to this. Apply the field to this. Fine. When you apply the positive and negative centers, so these molecules which are randomly aligned before, so these were aligned randomly. Let us say this is like this, this is like this, this is like this. Okay, this is like this. So these will align in one direction. What is happening? It is aligning in one direction. Right? So what is happening? The polarization is happening over here. Okay, now it is polarization is taken place, right? By application of, here it is E is equal to 0, here E is greater than 0. When apply, the field is going to happen like this. Okay, so this is the single molecule. This is single molecule which has the dipole moment now, and the single molecule has its field, its own field. Okay, what we are applying is, it is external field. So plus and negative, this we are applying the external field to this. Due to this external field, these all molecules have aligned in one direction. Fine. And each and every molecule has its own field now. Okay, that means what, I have taken this molecule like this, right? It has got its own negative and it has got its own positive. What it means, it is having the poles negative and positive. That means it has got its field. So there will be field between these 2 points. There will be field between these 2 points. There is a field between these two points. Okay, that field is called as EI. That is EI. And this field at this point, which will influence on this, which is influencing on this, which is also influencing on this. That means this single molecule has the influence on all the molecules, which has got influence on the all the molecules, and this is called as EI, is the internal field. Okay, what it means is, the field at any atom, the field at any atom is equal to sum of applied electric field, sum of applied electric field and electric field due to the surrounding dipole moments. Okay, so it has got its own field, and at this point, what is the field is, field is the field due to external field plus. Okay, so this is going to influence on this, this is going to influence on this, so it is going to influence on that. So this is a single molecule. On this, all the molecules have its influence. Okay, all the molecules have its influence. That means at this point we have some extra. So this is external field, this is external field which we have applied between these two plates, plus we are going to find out what is the internal field here. That internal field will be more than the external field. Okay, this is something amazing. Fine. So what we feel is, what I have applied here between two plates, that is external. Okay, but additional, what is additional, what is additional, additional is, this is going to influence on this, this is going to influence on that. Okay, the sum of this, sum of this. Okay, here it has got some electric field, so these all together having some electric field. So these electric fields also influence on this atom, single atom. So this is called as internal field. That internal field is EI. EI is equal to, okay, EI is equal to the sum of applied field, applied field, okay, plus the field field due to surrounding surrounding dipoles, surrounding dipoles. Okay, so did you understand? This is the internal field we are going to find out. Internal field means the what we have applied, that is external, the applied field, external applied field, plus the field due to surrounding dipole moments. Okay, the field due to these all other atoms which are influenced on that, that is also this. That means at this point, the field is greater than the applied field. What we are applying externally, the field at this point, it is greater than the applied field. Okay, this is called as the internal field.